In this video, we will try to understand the basic concepts of networking, specifically to IPv4 addressing. Now, the content of this video is not directly related to MuleSoft, but it creates a foundation to understand the networking concepts in CloudHub. So here's the agenda. We first start with the IPv4 basics. This involves understanding of the IPv4 addressing format and basics of decimal to binary conversion. Then we move on to the IP address classes. We discuss class A, B, C, D, and E in detail. Followed by that, we will understand what are private IP addresses and why this address needs to be translated into public IP, and that is done by network address translation. Finally, we try to understand subnet masking, which is the foundation for classless interdomain routing, also known as CIDR. Now, just like the real world addresses, computers in a network also have an address so that they can send or receive data. The only difference is that computer addresses are expressed in decimals or binaries. So let's understand how it is done. Now an IPv4 address is always 32-bit long and set of each 8 bit. So this 32 bits are divided into 4 sets of 8 bit. So it form each 8 bit is called as an octet. Let's understand that with the help of an example. So here's an example. Now this example has decimal, binary, and conversion. So this is a typical IP address 192.168.0.1. I have converted it into binary and the logic for conversion is also shown here. Now here's the exact values that are being used. Now let's understand this example in detail. The first thing that we should observe is that 192.168.0 and 1, these are all decimal and are all separated by a dot, although the dot is not shown here, but each of this set is separated by a dot. Okay, now why is it 32-bit long? Because once we convert this whole value into binary, it turns out to be 32-bit in length. But we don't convert at once all the values, we convert a part. Each part is converted separately. So if you see 192 is converted into binary, 168 is converted into binary, 0 is converted into binary, and 1 is also converted into binary. But the binary conversion is 8-bit in length. So each part, so there are total 4 part and each part is 8-bit in length. So 8 into 4 turns out to be 32. So that is the reason an IP address is 32-bit address. Okay, and each part of 8-bit is called as an octet. Alright, so even if no matter what the length of number is, if it's 0, if it's single digit or anything, it has to be in 8-bit. So even if you fill it with 0, that's not an issue, but it always needs to be represented in the form of 8 bits. Now, since we are using binary, we are converting decimal to binary. So decimal is base 10, binary is base 2. So if you want to convert decimal to binary, we use the power of 2 because it's base 2. And here is the conversion. So it starts from 2 to the power 0 until 2 to the power 7. So total 8 places. And now let's understand how we convert this 192 to binary. So to convert this, always keep in mind, always have this table ready. So 192 is greater than the highest value available in this table. The highest value is 128. So we can easily subtract 128 from 192. So if we subtract 128 from 192, we are left with 64, right? So since we subtracted 128 from 192, we can place a 1 at this position, which is the 7th position. So that is what we have done. We have placed 1 at the 7th position. Now what we are left with is 64. Now let's search for 64 in this table. Do we have 64? Yes. So we can subtract 64 from 64, which will turn out to be 0. So we can again place 1 at this position, which is the 6th position. So 1 and 1. So if we sum up these two values, 128 and 64, turns out to be 192. So since we have achieved 0, there's no more digits we need. This is done, right? So 128 plus 64, we already got 192. So the remaining places, can be filled with zeros. So that is what has been done. 1, 1, and the remaining places, 6 digits are or bits are set to 0. Let's move on to the other part, which is 168. Now again same thing, 168. Let's search. Is there any 168 here? No. The highest possible value is 128. So of course we can subtract 128 from 168, and while doing so, just make this as 1. So that's being done here. It's 1 because we are subtracting, right? So we can easily subtract. We kept it as 1. Now 168 minus 128 leaves us with a remainder of 40. All right. So now search for 40 in this table. Do we see any 40 value? There's no 40, right? So what we can do is we can search for a value which is lesser than 40. 64, it's not less than 40. So we cannot subtract 64 from 40. We can, but we will get a negative remainder. So that's not possible. So let's move to the next value. Is 32 less than 40? Of course it is. So we can subtract 32 from 40. So put a 1 at this place. So that is what we have done. 2 to the power of 5 is kept as 1. And since we could not substitute anything for this, we made it as 0. So now 40 minus 32 leaves us with 8. Okay, so we have 1, 0, 1. Now 8 minus 16 can be done, but we are left with a negative value. So we cannot subtract this. So put a 0 in this place. So that's what is done. It's 0. Now 8 is already there, and this is what we needed. So 8 minus 8, 0. So we fix 1 because we needed this. So this is 1. Now we have reached 0. So we need not think about the rest of the part. We can right away put zeros in the remaining digits. Okay, so what we concluded here, so if we check this position, 128 plus 32 plus 8, we get 168, right? So that is how we converted 168 into binary. Similarly, we have 0. Now 0 is quite obvious. You don't need to fill any of the places with any bits. It's 0. And finally we have 1. Now search for 1. It's already there, and 1 minus 1 is 0, which means that we have the 0th position fixed with 1. So this is how you can convert a decimal to binary or a binary to decimal. And always remember that an IPv4 address is a 32-bit address, okay, and each set of 8-bit is called as an octet, and it will have total 4 octets. Now that we have understood the IPv4 address formatting, the binary and decimal conversions, Let's move towards the IP address classes. The first one is class A. It starts with a binary 0. Now what does that mean? It means that the first digit of the first octet is set to 0 and cannot be changed. The remaining 7 bits in the first octet can have various combinations of zeros and 1. And we'll try to understand this with the help of an example. Now, if we talk about the decimal range, it starts from 0.0.0 to 127.255.255.255. Now, you might be wondering, why is the 0 in red and the remaining in a different color? Now, let's try to understand that. So, here's another example wherein I have made a binary representation. Everything is 0 here, but it's just to show the representation of octets in the form of 4 octets. Now the red part defines the network portion and the blue part defines the host portion. So in any IP address, you have two portions. One is the network and one is the host portion. Now you can think of a network as a street name and host as a house number, right? So a network can have multiple hosts, okay? And when I talk about this host portion, this can have multiple combinations of zeros and ones, but the network portion for class A is fixed until the first octet, all right? And it can range from 0 to 127. Now let's understand this with an example. When I talked about the first point, which is starts with binary 0. So if you observe, I have two parts here, first octet binary and the decimal conversion of that first octet. We are only concerned about the first octet because that defines the class A address and that defines the network. Others can have their own combinations. Okay, so the first octet binary. Now, when I say starts with binary 0, so it's that the first bit or the seventh position bit when it's starting from 0 is fixed to 0. It cannot be changed. So the start and end is fixed to 0. And then the remaining combinations are possible. So the starting would always be 0 and the end, if it's ending, then it has to be 1. All the bits are filled with 1, but the first bit remains 0. So plain conversion to decimal is 0 and the conversion of ending address to decimal is 127, which means that it can start from 0. The first octet can start from 0 and end until 127. Now if you observe, this part is reserved and this part is also reserved, which means that if there is an IP address 0.0.0.0, this is reserved. All right. So, and also any IP address starting from the series of 127 is also reserved. So any IP address now 0.0.0.0 or 1.0.0, 2.0.0, right? So starting from 0, all will be reserved. So if it is 0.1.1.1 until here, this all is reserved in decimals. Now I'm talking about decimals. Now, but if it's 1.0.0, it's not reserved. So actually we can use from 1.0.0 until 126.255.255.255, because after 126.255.255.255 you'll have 127.0.0. Now what is this reserved thing? So this 127.x.x I mean 127.0.0 or 0.1.0, 0.0, any combination of the values after 127 are reserved for loopback address. So if on your machine, if you host a web server or start any application, all right, and if you use this IP address 127.0.0 or 127.0.0.1 or any combination in this XX, but first has to be 127, it will call the same server. Hence, it's a loopback address. So all this 127 series is completely reserved. Similarly, the 0.x.x is reserved for the default network. So the effective values of IP that we can have starts from 1.0.0 in it's in decimal, okay? So starts from 1.0.0.0 to 126.0.0.0. So that's the usable IP range in class A, and the rest of the IP range, this special thing, these are all reserved. On the similar lines of class A addresses, we have class B address. Even C is also on the same line. So class A address was having first bit of the first octet set to 0. Now it changes slightly for class B. Here we reserve first 2 bits of the first octet, and the first bit, which is the 7th position bit, is replaced with 1, and the next one, which is the 6th position if we start from 0, is having 0. So 1 and 0 is fixed, and you can have all possible combinations of zeros and ones for the remaining 6 bits in the first octet. Now here's the decimal range. It starts from 128.0.0.0 to 191.255.255.255. This 255 is the max limit when all the 8 bits of an octet are set to 1. Now again we have the binary representation. It's not exact but just a format so that you can understand the network and the host portion. So the network portion here is the one in red and the host portion is the one in blue. Observe that as opposed to the previous class A address, we now have 16 bits as the network. Previously it was just 8. And the host portion has been reduced as well. Earlier it was 24 bits, now it's 16. Now just to give you an idea of the network and the host part is the actual machines that can be in a network. And network, you can consider it as a router. A router can have multiple machines connected to it, right? So network determines the number of routers, or assume gateways that can be in the connection or in a network. So that's network, and host is the actual machines which are connected to a particular network. Now let's quickly come to the binary and octet decimal conversion. So the first octet binary is what we are considering, and that's same for all other classes as well. So first octet binary, as we said, 1 and 0 is fixed, so same 1 and 0 is fixed, and all possible combinations are allowed. So starting would be zeros, right? So we set all the remaining 6 bits to 0, so it turns out to be 128 in decimal, and that's the starting point. Here there is no reserved address as such. There is a special class of address though in each of these classes, special set of address, but it doesn't have any reserved IP address the way it was in class A. And this is the end maximum value for the first octet, which is all ones. for the remaining 6 bit, and it turns out to be 191. So that's about the start and the end point, end IP of the class B address. Now it has subnet mask of 255.255.0. Now I didn't discuss this in class A, but it's good to know that, and we'll discuss this in detail on the subnet slide. But right now you can assume that a subnet mask helps you to find out a network and the host portion. When you see a subnet mask similar to this, wherein 255 and 255 is populated, you can assume that the first two bits are the network portion and the remaining zeros are the host portion. You can also call it as a mask of 16 because the first first two octets are reserved for the network. Similarly, the subnet mask for class A would be 255.0.0.0 because we just had first octet as the network. So if we can also represent it as subnet mask of 8 for class A. For class B, we can say subnet mask of /16 because the first 6 bits are reserved for network and remaining can have host. Now here is a sample IP address from class B. So 172.16.0.1. So this is the host network portion and this is the host portion. All right, and yeah, the pretty much binary conversion, you should be able to do it now if you have followed the first slide correctly. Now let's move on to class C addresses. So until now, the first two bits or the bits at the 6th and the 7th positions of the first octet were fixed to 1 and 0. Now this is slightly different. Here we have increased to 3 and the first two or the 7th and 6th positions of bits are fixed to 1 and the 5th position starting from 0 is fixed to 0. So it will start with 1 1 0 in the first octet. Now the decimal range is 192.0.0.0 to 223.255.255.255. Now even the network portion will increase now. It will be the first 3 octets and the remaining portion, which is the last octet, is the host portion, which means that this particular type of address can have at max 255 IP addresses. So any network that is formed in class C can not have more than 255 IPs, right? Because the only possible combination for this would be 255 from starting from 0 to 255, right? So it won't have any more IP addresses than that. So at max, one network in class C can have 256 devices connected. Now let's talk about the binary and decimal conversions. So we only talk about the first octet and the binary and decimal conversion. So again, 110 is fixed as we said, and the remaining bits can have all possible combinations. So the remaining 5 bits are there. So the first one would be obviously you fill the remaining positions with 0. It becomes the first position. So it starts with 192. And to get the last one, you fill all the remaining position with the maximum value, which is 1. So it ends in 223. Now it has a subnet mask of 255.255.255, which means that it also can be represented as /24, right? Because the first 3 octets are the network portion. So it's /24. And here is an IP address which is part of class C. So it's 192 and the binary conversion. And if you observe, the first 3 octets are the network portion, and the remaining last is the host portion. Now, class D is a special category of IP address, and it has all the multicast addresses. We won't be using class D and E much because these are special classes of addresses. What's important to know is A, B, and C. Now it starts with 1, 1, 1, and 0. So again, there has been an increment here. So it's 1, 1, 1, 1, 1, 0. And the decimal range starts from 224.0.0 to 239.255.255. And here's a typical binary and the decimal conversion for class D. Now let's move on to class E. Class E is again a reserved space of IP addresses, which means that any commercial network cannot use class E addresses. Those are reserved for experimental purpose. Okay, so it starts with all binary ones, at least in the first 4 bits of the first octet, and the decimal range is from 240.0.0.0 to 255.255.255. So this is the last uh, address of IPv4 because all the octets are having ones, right? So this is the binary to decimal. So first 4 bits set to 1 and the remaining 4 bits set to 0. So its equivalent is 240, and then 255 is all the bits are set to 1. So until now we understood class A, B, C, D and E IP addresses. One drawback that this addressing system has is that the effective IP addresses available for usage is quite less. Take the fact that class A has the loopback and the default network reserved. Class D is reserved for multicast and class E is reserved for experimental purposes. So the number of effective IP addresses is quite less. Now, given the fact that the number of internet users are growing exponentially, we might soon run out of this IPv4 ranges. Hence, to tackle this problem, private IP addresses were created. Although currently we have IPv6 coming up and it's already in use, but at that point of time, this was a solution. So these private IP addresses are not routable to the internet. So you will never see any public IP which will be among the list that I'll show you now. So it's not routable to the internet. Any traffic coming from such IP addresses is automatically dropped. Now, since these IP addresses are not routable to the internet, they need to be converted to public IP addresses so that they can access the internet. So that can be done with the help of network address translation or netting. Now here is the list of the private IP addresses. Now if you observe, there are 3 type of private IP addresses. One starts from 10.0.0 and ends on 10.255.255.255. This means that this is the part of class A addresses. So this part is reserved now again in class A address for private IPs. The second one is from class B and the third one is from class C. Now all of these IP addresses can not directly access the internet. They need someone to translate this IP. So usually, even if you currently check your IP address of your laptop, as long as it's connected to a router, it will have an IP address from one of these classes. All right, and then the router, which is connected directly to your ISP will have a public IP, and the router's job will be to convert this private IP to a public IP, and using that public IP, the device can access the internet. We'll try to understand this network address translation in detail in the next slide. Now let's understand network address translation in detail. Assume I have three computers in my office, and all of these three computers want to communicate with each other. So it could be that this system needs to access a database which is present on machine 2, and the system also might want to access a file which is on machine 3. So in that case, this machine needs to interact with this as well as this machine. So they need to be connected. Now, from a basic perspective, what you can do is simply link a cable on the LAN port and then connect these two machines, and similarly connect this one with the second with the third, and all three will be connected. But that's not how usually the networks are configured. Instead, these machines are connected to a router. So when a router comes into picture, it creates its own network. So by default, the router will have its IP address set. Now, this IP address is a private IP address from belonging to class C. Now, and all the standard routers will always have a private IP configured by default, and obviously you can tinker around the settings as well. So once the router comes in the picture, it has its own IP address. Now, if other systems want to connect to it, the router assigns an IP address to them as well. So this machine has got an IP address of 52. Similarly, the second machine after connecting gets an IP address of 54, and the third one gets an IP address of 56. Now all the three machines are connected using the router, and this machine can easily access the machine at address 54 and 56. So using the required or relevant protocols, they can access the resources available on each other's system. So until now things look good, but what if these machines want to access something on the internet? So someone might want to access a public API, or possibly a YouTube video, right? So this is currently a local network. It has no access to the outside world. These machines are only interconnected with each other. So they need to be connected to the internet. So to connect to the internet, this router needs to be connected to an ISP, and this ISP is usually will lease out a cable line, and that line is connected to the WAN port of the router. So once that WAN port is connected with the cable from the ISP, in that case this router will get a public IP, and using that public IP, these machines can access the internet. Now sometimes situation could be different. For example, this router is again connected to another router, right? So this particular router can be, in most of the cases it usually happens that your ISP leases out a network, and then the local players in the market, they connect to the big players, and they use their own equipments to get network, and then they lease out a line and they assign it to different subscribers. So this is just a typical example. So here this antenna is receiving signal from the uh, main sector Okay, so this is a sector, and this sector is emitting the signals, and both are transmitting and receiving the signals. So consider this is also a router, this is also a router. So now in this case, this router needs to communicate with this router. Now this, since this is also a router, it will have its own network. So it has its own IP 192.168.88.1. Now remember, this is a class C address having a natural mask of 24. So, so this part is the network portion. So this is a different network and this is a different network because it has 188 in the third octet and this has 0 in the third octet. So both are two different networks. All right. But now to access the internet, this router, wireless router, needs to connect to the ISP. So it can either connect wirelessly because this is a wireless router, so it will connect wirelessly, or had it been a wired connection, so they might have leased a cable and you could have connected directly to this router. So now since this is a wireless example, this guy will have a public IP address assigned to it by the ISP. All right, so this has a public IP now. Now, if this systems want to access the internet, how does it work out? Suppose this machine wants to access youtube.com. So the request goes to this machine, which is the router. Okay, so this IP address of 52 will be translated to this IP address. So 168.0.1, and this router will take this request to this router, and this router will realize that okay, 192.168.0.1 wants to access youtube.com. Same request will be taken by this router and it will be forwarded to the ISP. All right, and the IP address that would be visible to the other systems on the internet would be this IP address, 117.195.128.15. The moment any response is received back, so this router will now see, it will check there's a routing table. So it will check that routing table, what is the value. So this is how the routing table looks like. So this IP address, this router knows that the request for youtube.com came from this IP address. So it sends it back. Now this router also has a table, okay, and it knows that youtube.com was requested by 192.168.0.52. Okay, so the response will be sent back to this machine. So that is how things work. So eventually when someone at youtube.com is trying to understand from where the request is coming, what they can see is only the public IP address. They don't know anything about the internal network. Same happens for this router. This router does not realizes who is requesting for youtube.com. It's machine A, B, or C. It only knows that this router is asking for youtube.com. Only the only system that knows about from where the request is coming is this router, because these machines are connected to this router and this router is keeping track of all the translations. So all these IP addresses will eventually get translated to 192.168.0.1, and this router will only be able to see this particular IP, and eventually this particular IP gets converted into this private IP and then later on to a public IP, and using this public IP the internet access has been enabled. So this is how the routing table looks like. Now in simplified cases, usually if there is a line coming from the ISP directly to the router, this router would have got the public IP right away rather than this particular element in between. So this is how the table is maintained. So all of these three IP addresses first get converted into so here's there's a correction, it should be only one. Okay, so it gets converted into 192.168.0.1, and later on it gets converted into the public IP, which is 117.195.128.15. So this is how internet is accessed. Now other thing to notice, so I have just used the command prompt to check the IP config, and if you observe, so this is the machine on which I have checked the IP config. So it's 192.168.0.52, so same is the IP address. And if you observe the subnet mask, it's 255.255.255.0, which means that it has a mask of 24. So it has only this portion as the host portion, and the remaining part is the network portion. And the default gateway is set to 192.168.0.1, which is the router. This machine cannot see this router, so that is why you are not able to see anything. Only this router has the visibility to this machine, which is the external facing router. So that is how the translation is taking place. Since this private IPs cannot access the internet, they are eventually translated to a public IP by the router. Now, if you directly connect the WAN cable to the WAN port of either of the machines, they right away get the public IP and there's no translation required. But translation is necessary because we cannot have thousands of machines having public IP, because there is a lack of public IP, right? And even if we have a public IP for all this machine, then we need to have a huge pool of public IPs, which is not practical. So at least for individual customers, it's not practical. For business, they can have a requirement, but for a common consumer, it's wise to have only one single public IP, and then they can connect multiple systems like your mobile devices, laptops, computers, smart TVs, right? So it makes sense. All of them have a private IP, and then later on they translate to a public IP using which they can access the internet. Now let's understand subnet masking. Now, we have already discussed about subnet masking to certain extent in while discussing class A, B, C, D, and E IP addresses, but here we'll understand in detail about subnet masking. So, subnet masking helps to identify the network and the host portion. So, if you're aware of the different classes of IP addresses, then you might not need subnet masking, but anytime if you check the IP config, it will always show you the subnet mask. Like the way we saw in the previous slide, we were able to see a subnet mask of 255.255.255.0 for a class C IP address. So that's the use of subnet masking. Now, classes A, B, C have natural mask of 8, 16, and 24 respectively. So a natural mask of 8 determines that only the first octet is the uh, network part, and the remaining 3 octets are the host. Similarly, 16 means the first 2 octets network and the remaining 2 octets host. 24 means the first 3 octets are the network part and the last octet is the host part. Same has been represented here in the form of binary and the decimal format. So a subnet mask of 255.0.0.0 implies that the IP address belongs to class A, and this is the binary conversion. So the first octet is populated with only binary ones and the remainings are left empty. So this is the host portion and this is the network portion. Similarly for B and C. Now, subnet masks can have contiguous series of ones. Discontiguous subnet masks are not supported by the routers. So a discontiguous subnet mask means like here everything is continuous one, right? So if you have a zero in between, that is not supported. So all the subnet masks have continuous series of one. Now this point will add more value when we discuss about CIDR in detail in the upcoming slides. Now let's understand the problems with classful IP addresses. Okay, so a class A IP address has a subnet mask of 255.0.0, which means that the first octet is reserved for the network portion and the maximum number of hosts that can be occupied is the remaining 3 octets, which calculates to almost more than 16 million IP addresses available in class A addressing. Similarly, for class B, since the network portion here increases as the subnet mask is 255.255.0.0, obviously the number of IP addresses or the host that can be allocated reduces to 65,534. Similarly, the least number of hosts that can be allocated is for class C because the subnet mask is 255.255.255.0. So which means we have only the last octet left for the number of hosts. So it turns out to be 254. Now you might be wondering what's the problem in this? So it looks good. The only problem is that what if I need 500 IP addresses? Which of these classes will I be able to choose? Or for that matter, take any number of IP address. Suppose I need 255 IP address or 256. So I don't have any close range. After 254, it's directly 65,000, and after 65,000, it jumps to 16 million. So if I had to add 500 IP addresses, I have no option but to choose class B IP addressing, and it gives me 65,534. So this eventually leads to wastage of IP addresses. Now add to the fact that we can't even use class D and class E, and even in class A, as you might have seen in the first slide, we had couple of ranges reserved, right? So there's a lot of wastage of IP with this type of assignment, right? To solve this problem, classful IP addressing was removed and there was a new solution named as classless interdomain routing, which is called as CIDR. Now let's discuss that. So now we are finally on CIDR. It's classless inter-domain routing. So this is a notation as well as a solution to the classful IP addressing. So what does it help to attain, right? So it allows us to have variable length of subnet mask. So if we get variable length of subnet mask, we can have different ranges of IP satisfied, right? Because if we see A, B, and C, the natural masks they had were 255 first octet reserved and the 3 octets available. So the IP ranges were quite the growth of IP ranges was quite exponential, and we were not able to serve a specific set of requirement, right? So this variable subnet mask length allows us to save the IP addresses. Now, if we see class A, we have a subnet mask of 255.0.0. All right. Now, if we had to express this in the form of CIDR, now CIDR is also a notation, okay, and it also allows you to have a variable length subnet mask. So if we were to represent this in the form of CIDR notation, we would express it as /8, which means that the network portion should be 255. So /8 tells you the network portion. It says that the first octet or the first 8 bit will be filled with binary ones. So assume this has to be the number of bits starting from the left hand side, which will be filled with binary ones, and that will be a network portion. Similarly, for class B, the CIDR notation would be 16 because it will have 16 binary ones starting from the left hand side. For class D, you can guess it, it will be 24 because it will have first 24 bits as the network portion, and it will be total 24 bits, right? Now, CIDR is not just a notation, but it will allow you to have variable subnet mask. Okay, so it can allow you to have a subnet mask of 1, 2, 16, 15, 23, and so on. So it's variable, thereby helping you to save IPs. Now let's understand that. So now that we have understood the CIDR notation, let's try to figure out the CIDR notation for a given IP address and a subnet mask. So here is a screenshot from a system which has a particular IP address, uh, which is 10.150.116.43, and this is the subnet mask. Now if you observe, the subnet mask is slightly different than the ones that we have been observing, because usually we used to have whole octets, which is 255.255, and here also 255, but now it's 240. So it's slightly different. Now let's try to figure out how can we determine the CIDR notation for this particular subnet mask. So as a thumb rule, what you can do is just take this subnet mask and convert it into binaries. So here is the conversion of the subnet mask. Now once you convert it into binary, just check on the octet where you see it's not 255, right? So it's I mean, the boundary of separation between the network and the host portion lies somewhere in the third octet. This should be quite visible to you if you have followed the video properly until now. It should be easily understandable that this is not 255, and the network and the host partition lies somewhere around this portion, the third octet. And if we see in the binaries, we see that everything is 1. Over here, we see that here is the partition. So in the third octet, we see that only 4 bits are 1 and the remaining 4 bits are zeros. So this part is the network portion, and the part in blue is the host portion. So what would be the CIDR notation for this? So to calculate that, you can simply check the number of ones. So 8 plus 8, 16 plus 4, 20. So it's 20. Now if you practice it more, you would realize that this, by watching this, you can easily say that don't need to count for this. This is 8, this is 8, so it becomes 16. You only need to count for this particular 240, and the number of ones that you encounter, continuous one. It should not be 1011. It should be continuous one from the left side. You add those number of ones to the existing ones. So 8 plus 8 plus 4. So it becomes 20. So 20 is the CIDR notation for this network. So in the last slide, we found out that the CIDR notation for this particular network turned out to be 20. Now, with that data, we can find out the first host, the last host, the network, and the broadcast address. And based on this, we can also figure out the number of IP addresses this network can have. So let's start with that. So here is a sample table. What I have done is I have just taken the IPv4 address of this machine. You can also find out using the ipconfig command on your command prompt and get the IP address and the subnet mask. So we found out based on this subnet mask that the value for CIDR notation was 20. Okay, so just convert this decimal to binary and mark this red portion based on the value that we found in previous slide. So it was 20 bits. So we selected the first 20 bits starting from left hand side, and this is the boundary in the third octet. So these are the first 20 bits which determine the network portion, and the remaining bits, which is 12 bits, determine the host portion. Now, if you want to find out the network part, what we have to do is we just fill the host portion with binary zeros and then calculate the decimal equivalent. So that is what I have done in the next row. So this is the network, and I have filled all the host values with binary zeros. So what does it turns out to be? So the network turns out to be 10.150.112.0. So this binary converts to 112 in decimal with a CIDR notation of 20, of course. The first host, if you want to calculate the first host, keep the network binary conversion same as is. It's just that you add a binary 1 at the last bit of the fourth octet. So this calculates to 10.150.112.1 in decimal. Now, if you happen to calculate the last host, it's pretty simple. You keep the host values as 1 everywhere, with an exception that this last value has to be made as 0. So all of this value become binary ones, and the last digit of the fourth octet is kept as 0. So this calculates to 10.150.127.254. Now, if you want to find the broadcast address, it's simple. Use the last host, just make this 0. It will be 0 for last host, make it as 1. So the broadcast would become the same address, with just that the last octet would be 254. Now, if you are supposed to calculate the total IP addresses, just use this formula: 2 to the power 32 minus the CIDR notation, which was 20 in our case, minus 2. The reason we are subtracting this 2 is because the first IP is reserved for network and the last IP, which is 255, is reserved for broadcast address. So we are reducing 2 IP addresses from whatever we are getting. So it becomes 32 minus 20 becomes 12, 2 to the power 12 becomes 4096, 4096 minus 2 gives us 4094 IPs, which means that we can have 4094 hosts in this particular network. So in this manner, you can find out the first host, last host, the network, and the broadcast address. Now, if you closely observe this table, you can see that you don't even need to calculate the first two octets. They remain as is, right? 10.150. So everywhere you can see 10.150. The only place where you need to do binary conversion is the octet, where you see that there is some difference where in the octet where you see it's not 255. So here you realize that it's 240. So the network and the host partition was somewhere in the third octet, and that is what we have done. We just played around with the third and the fourth octet. We didn't even touch the first two octet. So we could have kept this as 10.150, not have bothered about this, just worked on the third and the fourth octet. So that is how you can use the CIDR notation and figure out what would be the network, what would be the CIDR block that you can use for having a particular set of IP address. You can always use this formula to calculate the number of IPs that you want based on the CIDR notation. And if you want to find out network first host, last host, this is the method. But then you should you should be aware of what is the subnet mask. This technique is for existing network wherein you want to find out this detail. If you are creating a new network, you can right away use this formula and based on this formula you can figure out the number of hosts, and then you can use the same technique to find out the host details. So that's all for this video. I hope you found the video useful. Thanks for watching.